In this video, I want to talk about composite tests. So tests for hypotheses where you don't just have simple versus simple. So one of our hypotheses will allow for more than one possible set of parameters. And we'll have an example of this where we derive a t-test, which I think is a really, I don't know, it's good for you to see where t-tests come from. So we're going to be doing a t-test, so that means that we're thinking about normally distributed data. So suppose that we have x1 through xn, which are independent and identically distributed with a normal distribution with mean mu and variance sigma squared. And so in this setup, we're going to arrive at a t-test, and t-tests are relevant when both mu and sigma squared are unknown. So that means that our full parameter vector is the vector of both mu and sigma squared. So this is going to be denoted by theta, and theta is a vector, so I'm going to put a squiggle underneath of it. And theta is the vector mu sigma squared. I'm not going to keep track of whether it's a column vector or anything. The parameter space is the set of all possible values for the parameters. And remember that we're denoting that by omega. And so this is the set of values for mu and sigma squared, such that mu is a real number. So the mean can be anything, but sigma squared has to be positive. So that's the set of all possible values for the parameters of this normal model. And now let's suppose that we're doing a test about the mean of this distribution. So consider a test of about the mean. So the null hypothesis is going to specify a particular value for mu equals mu0, and the alternative. Now I'm not going to do simple alternative, so I'm going to just say it could be anything. So let's say that mu is just not equal to mu0 for the alternative. And so this is a two-sided alternative. We could have done a one-sided, like mu is greater than mu0 as well, but let's just do a two-sided example here to see how it works out. So remember that when I first introduced likelihood ratio tests, I said that in general, like it's nice, it's useful to be able to think about likelihood ratio tests in terms of specification of sets that the parameters belong in. And here I've just said something about the value of mu, but there's also another parameter, sigma squared. So to be more formal about this, I might write these hypotheses another way, which is I might write the null hypothesis is that theta, the vector theta, which has both mu and sigma squared in it, is an element of a restricted parameter space, omega 0. And this is the set of values for mu and sigma squared. And now I'm placing a restriction on this so that mu is equal to this value mu0, and still sigma squared can be anything that's positive. And the alternative hypothesis is specifying a omega a for alternative. And this is the set of values for mu and sigma squared such that mu is not equal to mu0 and sigma squared is bigger than or equal to 0. So the generalized likelihood ratio statistic is like just the likelihood ratio statistic, but what do you do with it if your alternative hypothesis doesn't specify a single value, but specifies a whole set of possible values? Maybe I should start by reminding us of the likelihood ratio statistic. So for the likelihood ratio statistic, we said that this is W, and this was the likelihood of theta 0 given x1 through xn, divided by the likelihood of theta A. And so this is relevant if we have simple versus simple hypotheses, because then you have a value for omega 0 and a value for omega A. So then the question is, how do you adjust this for the setting that we're looking at now, where you have sets of values? And so the way to adjust it is with a generalized likelihood ratio statistic. And this is useful for composite hypotheses. And the setup is very similar, but now I want to choose the maximum I want to basically maximize the likelihood subject to the restriction in the numerator that theta is in the set of values consistent with the null hypothesis. So it's just like above, except now I don't have a single number, theta 0, to plug in. And what I want to do instead is find, subject to the constraint that the null hypothesis is correct, what's the best possible value of theta subject to that constraint. And then for the denominator, it's the same thing. And actually, so I guess maybe we can write just theta in omega, so not omega A here. So now the denominator is just going to be, out of all possible parameter values, what is the maximum value of the likelihood? And just to note that this definition that I'm giving here is good enough for our purposes. If you've taken real analysis, the really technically correct definition should be the supremum instead of the maximum. But not everyone has taken real analysis. So I'm just going to stick with maximum, which is good enough for today. And so just in words, this denominator is the maximum of the likelihood function. And the numerator is the maximum of the likelihood, but constrained to the null hypothesis set. So it's the maximum of the likelihood subject to the constraint that the null hypothesis is true. So we're going to base our tests for these hypotheses on this generalized likelihood ratio statistic. So let's do that for our normal example. And it's easier to think about the denominator first. I guess we've previously analyzed found the maximum likelihood estimates for the normal distribution based on a sample of n observations. And so for the denominator, we've previously found these results. So we've previously shown that the maximum likelihood estimators are mu hat, the estimator for the mean is the sample mean, and sigma hat squared is the usual sample variance, but with a divisor of n instead of n minus 1. All right, and then so that tells us like the values for mu and sigma squared to plug in to the likelihood function to find the denominator for calculating W, which we'll do in a second. And then for the numerator, we want to find a maximum, but subject to the constraint that the null hypothesis is true. So for the numerator, we're going to say the null hypothesis is true, and what that means is that mu is equal to mu 0. And we could do a little bit of calculus and show that, so based on that, we could show that the maximum likelihood estimator for sigma squared is sigma squared hat equals 1 over n, sum I equals 1 to n, xi minus mu 0. So we don't have to estimate the mean anymore because we're given it by the value specified in the null hypothesis. And so that means that we get to just plug that in, basically, instead of plugging in x bar. So I want to just take that as given. We could do that by taking derivatives. So this means that we're ready, basically, to plug these numbers, this mu hat and sigma squared hat, into the numerator and denominator to evaluate the likelihood, to calculate the likelihood ratio statistic. Before we quite do that, I want to first just figure out what the likelihood function looks like for this normal distribution so that we know what we're evaluating. So for a particular value of the parameter, so the particular value of theta, which means a particular value of mu and sigma squared, the likelihood looks like this. So I want the likelihood of theta given x1 through xn. I'm just going to write given x, the vector x. And really this means the likelihood of mu and sigma squared given x, which is the joint density for x given mu and sigma squared. And this, I guess I'm writing everything with capital X's, so I'm gonna stick with capital X's in here. And as usual, this is product I equals 1 to n, f of xi. And then we just need to plug in the PDF for normal distribution, which is, I'm going to write it as 2 pi to the negative 1/2, and then sigma squared to the negative 1/2. This is usually written as 1 over square root of 2 pi sigma squared, but just for convenience in our next steps, I'm going to write it like this. And then times e to the power of negative 1 over 2 sigma squared, xi minus mu squared, which is, simplifying the product, 2 pi to the negative n over 2, sigma squared to the negative n over 2, x of -1/2 sigma squared. And then I've got a product of exponentials. So there was a sum of these exponents, and then I factored out a -1/2 sigma squared. So I've got a sum I equals 1 to n xi minus mu squared in here. All right, so this is the form of the likelihood. And now what I want to do is calculate the generalized likelihood ratio statistic, which is a ratio of this likelihood with the maximum likelihood estimators plugged in for the denominator, and for the numerator with mu0 plugged in for mu, and this estimator of sigma squared plugged in for sigma squared. So the generalized, let's do that calculation. So the generalized likelihood ratio statistic is, I'm going to write this as capital W. So I'm thinking about the random variable likelihood ratio statistic right now. And then later, when we're calculating a p-value, we'll have a realized value of this statistic. So the likelihood ratio statistic is the likelihood. And in the numerator, I'm evaluating at mu0 and 1 over n sum I equals 1 to n xi minus mu0 squared, given the vector of data x. And the denominator is very similar, except instead of mu0, I've got x bar. So now I have, this is what I want to evaluate, basically. I want to evaluate in the numerator the likelihood at these particular values for mu and sigma squared. In the denominator, I want to evaluate the likelihood at these particular values for mu and sigma squared. So the way that I'm going to do this is take the expression that's at the top of the screen now, and for the numerator, anywhere that there's a mu, I'll plug in mu0. Anywhere that there's a sigma squared, I'll plug in 1 over n sum I equals 1 to n xi minus mu0 squared. For the denominator, I'll do the same thing, except anywhere there's a mu, I'll plug in x bar. And anywhere there's a sigma squared, I'll plug in 1 over n sum I equals 1 to n xi minus x bar squared. So let's do that now. Okay, so I've got a 2 pi to the power of negative n over 2. And then a sigma squared, but where there's a sigma squared, I'm going to put in 1 over n sum I equals 1 to n xi minus, for the numerator, mu0 squared. So that's my value of sigma squared. In the expression at the top of the screen, the exponent should be minus n over 2. And then times e to the power negative 1 over 2. And now here's a sigma squared. So where there's a sigma squared, I'm going to plug in 1 over n sum I equals 1 to n xi minus mu0 squared. And then we have sum I equals 1 to n xi minus mu in the expression at the top of the screen. And right now I'm evaluating the numerator, so I'm plugging in mu0 where there was a mu. So that's the numerator of this expression. For the denominator, I have a 2 pi to the power of minus n over 2. And then I have a sigma squared at the top of the screen. The expression I'm working with now is sigma squared to the power of negative n over 2. For the denominator, where there's a sigma squared, I'm plugging in 1 over n sum I equals 1 to n xi minus x bar squared. and then times e to the power -1 over 2 sigma squared. So for sigma squared, I'm plugging in 1 over n, sum I equals 1 to n, xi minus x bar squared. And then that is multiplied by sum I equals 1 to n, xi in the expression at the top. I have a mu. For the denominator, I'm evaluating the likelihood at mu equals x bar. Okay, so there's a lot of simplification that I can do now. The first thing I can cross out is the 2 pi n over 2's from the numerator and denominator. Inside of the exponent, if in the numerator, I've got a 1 over sum I equals 1 to n xi minus mu 0 squared, and that cancels with that same term there. So I can cross those two out. And similarly, I can cross those two pieces out. And then if you've done that, let's switch to a different color, then what's left here is e to the power of -1 over 2 times 1 over n. And in the denominator, there's e to a power of -1 over 2 times 1 over n. So those cancel out. So like that and that cancel out. And so all that's left basically is the stuff in the middle here. So the only thing that we didn't cancel out just now was this. So we'll keep that as we go to the next step. And then just to avoid confusion later, I want to note that like for this numerator, I've got something to a power of -n over 2. Let's just put that in the denominator with a power of n over 2 so that we don't have exponents that are negative. So I'm just going to rewrite this as basically swapping the numerator denominator and getting rid of the negative sign on the exponent. 1 over n sum I equals 1 to n x I minus, I'm swapping the numerator and denominator, so this should be a x bar squared. And now for the denominator, xi minus mu 0 squared. And while we're at it, I've got a thing in the numerator and denominator with the same exponent. So let's just say that I can group those and have an exponent of n over 2. All right, so this is the form for our likelihood ratio statistic, and we are now ready to calculate a p-value. The p-value is still calculated as the probability that the random variable likelihood ratio statistic or generalized likelihood ratio statistic, W, is less than or equal to the observed value of that likelihood ratio statistic, lowercase w, given that the null hypothesis is true. So just to be clear, this one is going to be the generalized likelihood ratio statistic, but as a random variable. So that means it's going to be based on capital X1 through capital Xn. And basically we're thinking about how could the value of this generalized likelihood ratio statistic change across samples. And this one, this lowercase w, is the generalized likelihood ratio statistic based on observed data. It's 1 through xn. And all of this probability is calculated on the condition that the null hypothesis is true, which really means that mu is equal to mu 0. So I'm going to simplify and write that next. All right, so let's calculate this p-value. And so just to be clear, we're calculating probability that W is less than or equal to lowercase w. And at the top section of the screen now, we found an expression for W that's simplified. So for the p-value, I'm going to want probability that W which looks like this, and the power of n over 2. So that's capital W. And then I want the probability that that's less than or equal to lowercase w, which is the same thing with lowercase x's in it. So 1 over n sum I equals 1 to n, lowercase xi minus my observed sample mean lowercase x bar, lowercase xi minus mu 0 squared to the power of n over 2. All of this probability calculated under the condition that mu is equal to mu 0. So what I'm going to do now is a lot of algebra. It's probably going to take about 5 minutes. And since you are watching a video, you're welcome to just skip ahead if you don't care about the algebra for a few minutes. If you are interested in the algebra, here goes. So I want to calculate this probability, and the first thing that I want to do is get rid of these exponents. So I'm just going to raise both sides to a power of the 2 over n so that the exponents cancel out. And so what I'll have then is, and I guess I can also cancel out these 1 over n's as well. So what I'll then have is sum I equals 1 to n, xi minus x bar squared, sum I equals 1 to n, xi minus mu 0 squared is less than or equal to that same expression with lowercase xi minus lowercase x bar and lowercase xi minus mu 0 squared. All right, and now let's flip these around for convenience. So what I want to do is invert these left and right hand sides. And as I do that, I'm going to have to switch the direction of the inequality. So what I want to do, just so that we arrive at the result we're trying to arrive at, is to make this so that in the numerator I have capital Xi minus mu 0 squared, and in the denominator xi minus x bar squared. In order to do that, I have to reverse the inequality. And the reason why I had to reverse the inequality is like if 1/5 is less than or equal to 1/3, then 5 is bigger than or equal to 3. All right, now what I want to do is use a result that we arrived at maybe 2 months ago or something, just some algebra. So previous results that I'm about to use is that if I have a sum like the one in the denominator here, or in the numerator, if I have a sum xi minus mu squared, this is equal to sum xi minus x bar squared plus n times x bar minus mu squared. So this is just some algebra. It would take 5 minutes, and we did it about 2 months ago. So I don't want to do it again, but I want to use this result. And so if I plug that in for the numerator, what I'll have is sum I equals 1 to n xi minus x bar squared plus n times x bar minus, in the numerator, I have a mu 0 squared. I'm basically just doing the things that I need to do to arrive at a t-test at this point. So that's the left-hand side, and the right-hand side is going to have sum I equals 1 to n lowercase xi minus lowercase x bar squared plus n lowercase x bar minus mu 0 squared. And all of this is given mu equals mu 0. And then I can do a little cancellation. So on the left-hand side, if we think about this, like I could split this fraction into 2 pieces by taking the numerator and making that into 2 separate fractions. And so if I do that, I'll be able to cancel out this one with the denominator, right? And so I'll have a probability that 1 plus, and now, okay, I'll just write it in 2 steps. N x bar minus mu 0 squared over sum I equals 1 to n xi minus x bar squared is bigger than or equal to 1 plus n x bar minus mu 0 squared over sum I equals 1 to n xi minus x bar squared, given mu equals mu 0. And then these ones cancel out on the left-hand side, on the 2 sides of the inequality. And I just want to manipulate these n's, once again, trying to get this to look like a t-statistic. And so a t-statistic should have like an n minus 1 in the denominator. We're aiming towards a sample variance, which is almost what we have in the denominator. And so I'm just going to take the x bar minus mu 0 squared in the numerator and move the n that was there in the denominator so that I have 1 over n minus 1 sum I equals 1 to n x I minus x bar squared over n. And then that is greater than or equal to the same thing on the right-hand side. All right, now we are just about at a t-statistic. The only thing that I need to do is take the square root. So this is going to be probability, And the square root of a squared number is really the absolute of that number, the absolute value of it. So think about like -3 squared is 9. The square root of that, I guess we're thinking about positive square roots, is 3. So I'm just going to write the absolute value of x bar minus mu 0 I guess I'm simplifying a little bit by thinking about absolute values, but it works out. It's basically less of a headachy way to think about the same thing. And then denominator, what we have is 1 over n minus 1, sum I equals 1 to n, xi minus x bar squared over the square root of n. And the same thing for the other side. All right, which is now pretty much looking like a t-statistic. So this is equal to the probability that t, this, I'm going to call this, yeah, okay. I'll write it more carefully in a second. So probability that t is either less than or equal to the minus absolute value of x bar minus mu 0 over the square root 1 over n minus 1, whoops, sum I equals 1 to n xi minus x bar squared over square root of n. Or that t is bigger than or equal to the positive square root. All of this given mu equals mu 0. And in this expression, where t is equal to x bar minus mu 0 over sample standard deviation as a random variable divided by square root of n. So the t statistic. So in picture form, we know that t, this random variable t, follows a t distribution. And so here's the t distribution. And it's centered at 0. And then on the left-hand tail, we've got the minus absolute value of x bar minus mu 0 over square root 1 over n minus 1 xi minus x bar squared over square root of n. And on the right-hand side, the same thing without the minus sign. All right, so basically we've just derived the t-statistic. Remember this whole thing, the t-test, this whole thing was a calculation of the p-value for this test. And so what we've shown is that the p-value is based on a t-distribution. So this curve is the PDF for the t-statistic, which has distribution t, degrees of freedom n-1. And we've shown that the p-value now is the area below and above the negative absolute value of the t-statistic and above the positive absolute value. So the combined area is the p-value. All right, so that's one last things that I wanted you to see in this class, basically like where does a t-test come from? And a lot of the other tests that you've used in other classes are also derived in exactly the same way. So an f-test for a linear model is also a likelihood ratio test. A chi-squared test is also a likelihood ratio test, and so on. So almost all tests that you use in practice are derived as likelihood ratio tests based on the generalized likelihood ratio statistic in this way.